And let me share my screen. Okay, before resuming our lecture, I just wanted to talk about something on assignment number 1 very quickly. And I have observed this in other assignments. I've been checking some assignments. And some of you left in this exercise this data open parenthesis function. And that is causing a problem with Quarto, right? Why? Because let me show you in RStudio what happens very quickly. Just wait some seconds here. Okay. Let me just close this. And actually, let me make this bigger, just in case it's too small. So when you use data open parentheses, it will try to open this list, right? But when you are using Quarto, Quarto is trying to open this tab. But the problem is that Quarto, the way R runs on Quarto is not interactive, so it cannot open the tab. So it kind of waits. It kind of waits for the user to do something. So that's when the Quarto document will tell you a warning or an error, right? So what is the solution? Just for assignment number 1, for those who are still working on that one, right? Just use it once, right? In order to check which data set you want to use, right? So let's imagine I want to use Johnson & Johnson, right? In your R chunk. And let's create a new document, right? Just for fun, just keep it there, right? So what you do is just to use, right, the name of the function and don't add data open parentheses. Otherwise, it will try to open that all the time, and your session, your Quarto session, the rendering process will stop. Or it might go on, but it will tell you a warning and you don't know what it is, right? Or if you want to keep it, you can keep it there, but just comment out that piece of information, right? That part of the code. So remember, inside inside our code, you can also use hashtag or numeric sign or this thing here, and this will convert this into text. So that means that R will skip this as a real command, right? And it transforms this into only text for R, and R doesn't do anything with that. So you can do this, and that will solve the problem, right? If you want to keep this for your records, right? If you want to keep data open parentheses in your homework, you can do it by just doing this, right? Just consider that, because I know that some of you are still working on assignment number 1. So just bear that in mind, right? If that happens, it's because of that. Yes, my pleasure, Laila. My pleasure. Yes, I know. I saw your email, and I figured that maybe other people might have the same problem, right? I remember I told you this in class, but I speak too fast and I talk a lot, and probably many of you missed the part when I mentioned that you have to remove data open parentheses from the chunk of code. Otherwise, the process will choke, right? Quarto will be trying to open this list and it cannot do it, right? So just to let you know that. Perfect. And here, let me go to, let me answer other questions that I have seen so far. I kind of have seen that some people are confused a little bit with the format that I follow in this practice number 2. And actually, by the way, I need to change the points. It doesn't make sense. Yeah, I don't know if you saw that. I mean, the questions are going to be the same, but the total points and the points for each question is different, right? According to our table of percentages. and the distribution of grades. So it should be a little bit more. So I'm going to change it later, but no worries, it won't affect your capacity to answer these questions. But I was going to tell you that some people, I think, got confused on what is Quarto and what I'm doing here, right? So some people ask me that, well, given that I can run this code, can I just copy this into a Quarto document without adding chunks? Well, the answer is no, right? So you have to add a chunk of code, right, to your Quarto document. You can copy this code, of course, right, and just add it to your Quarto document, right, into a chunk in order to make it work. The other question that I saw is that some people ask me, hey, given that I can run the code on the web page, can I just answer everything on the web page and you will see it? Well, the answer is no. Even though you are able to change the code, right? You are able to change whatever you want. For example, instead of call names, I can change this on the fly and run it again and use the function names. Or, right, you can change whatever you want because you are running a live R session online, right? I programmed that in a way that you can do that. So for example, here, I can do summary row, I don't know. See, oh, probably that's one, for example, right? And you will get different pieces of information. It's like working with R in your local computer. But even if you answer here, of course, I cannot see it because I haven't find a way to do that. I haven't found a way to do that. It would be awesome if you could answer everything here and it goes straight to a server where I see your answers. That would be wonderful. That's a wonderful idea, actually. The person who asked me about it, yeah, that's clever. I mean, that's the ideal scenario, but it doesn't happen like that, right? So you would have to just copy the code and do the Quarto document as you always do, or use your Word or Google Doc document, right? Like you always always did in the past, right? Because it might be confusing, right? Given that you can run the code, some people were like, "Oh, well, that's weird. Probably, you know, there's some technological thing that it can do," but unfortunately, not. Not yet. Not yet. In the future, probably, I will be able to program something that is more friendly in that sense, right? Like I will see everything on a server, and but it takes time to program that. It's not an easy task, especially if the person so especially like for somebody like me who is I consider myself like a amateur programmer. I like programming and I learn by myself. So it takes time to program those kind of things. So yeah, but in the future maybe, and that's a good thing to do. What else I was gonna say about this? No, I think that's it. I think that was everything that I needed to say. Mhm. Let me check. Yeah, I think those are the questions that I've observed so far. Oh, Denise, when you say run the code on the web page, I don't understand what page you. Yeah. Oh, Denise, that's a good question. I'm talking about practice number 2, right? If you go to the link for practice number 2 here on my website, actually, let me just copy and paste. Copy this link into the chat. Everyone in the meeting. Sorry, that's the web. That's a web page from my website, right? That's practice number 2. So when I say run this on the website, and what I mean is that you are able to run the code by clicking run right here, right? You can run the code on the website, right, or web page right here, like I'm doing right now, right? And look at that, it displays the output from this code right here, right? So that's what I meant by running the code on the web page. I meant to click run right here, and you can see the code. For future practice, this is going to be very similar. You will see chunks of code where you can actually run the code. And you could change it for fun if you want to. But still, you would have to answer the questions on a Quarto document or on a Word or Google Doc document, right? So this is still painful, I know, but believe me, that's way more useful for me to grade. And of course, you can change things here, right? That's what I meant. I don't know if that answers your question, Denise, or was a different type of question. Was that the question, Denise? Okay, okay. That's okay. That's fine. That's fine. Let me know if you have more questions. Of course, you can ask questions at any time. And of course, you can stay more time at the end of the class if you need to ask more questions. Any of you, of course. All right. So the last time we were talking about how regression is very similar right here. How regression is exactly the same as a t-test, right? The t-test, as I mentioned in my last lecture, is just a restricted version, a restricted model of a regression model. It's a restricted regression model. That's what it is. The technical name for that is nested model. It means that one model can be nested into another, right? It's like more like a Russian doll where you have different layers, right? So models, statistical models can be like that, can be like Russian dolls, right? One model is nested into the other. And at the end, they are part of the same theory, right? They are part of the same assumption. So t-test and regression is exactly the same. The only problem is that t-test is a regression with only one predictor. While in regression, you can add many predictors to your equation. Well, as many as information you have in your data set, right? If you have 20 people and you want to add 20 predictors, of course, the model will not work, right? Because you would have more pieces of unknown information compared to the amount of observations that you have, right? So, or even worse, let's imagine you want to estimate a model with 21 predictors and you have only 20 observations in your data set. It's impossible. There is no way that the model will give you something, right? It will crash just because it doesn't have enough information, right? Of course, there are limitations, but these limitations are related to the sample size. Okay, so I told you that, right? Hopefully that was kind of clear. We were talking about people with and without insurance, right? We saw that the intercept is the mean of group 0, and the slope, which is this part right here, is is the mean difference between group 0 and group 1, right? So we already mentioned that before. I'm just resuming, or well, just refreshing what we did the last time. I talked about dummy-coded variables, right? And I told you that those dummy-coded variables are very important if you want to compare multiple groups, right? If you have a nominal variable, like for example, race, right? In regression models, you need to transform this into a dummy-coded variable. And a dummy-coded variable is just a new variable, a new column in your data set that has zeros and ones, right? You will assign 1 if the person, for example, says she or he is black, and 0 if the person answer any other option, right? And the same for Asian, and the same for other, right? If somebody's Asian, it's gonna be 1, otherwise 0. If somebody says other, it's gonna be 1, otherwise 0. And that will create a matrix like this one, right? And remember, we don't need, in this example, I didn't need the white group, because the white group is my reference group, is my 0 group, right? So if everyone is 0, 0, 0 in all these options, well, by default, that person is white, right? So I told you that, and I gave you an example here, and we were actually, oh, it's in the other slide, sorry about that. Right here. And we did a regression model right here, right? If you scroll down, you will see the regression model, and you will see the mean difference, right? Of black people versus white people, the mean difference of Asians versus white, and the mean difference of others versus white. And we saw that people who said that they belong, well, they identify as other race, they are getting way less money compared to white people. And Asian people are actually getting more money compared to white people in this data set. And remember, this data set is only has only males, it doesn't have females. So we cannot make any inference about females in this case. So we don't know if this also holds for females, right? But it would be interesting to create another data set where we have both. And actually I'm working on that, on creating another data set with open source data from the World Bank. But it takes time. So I need to prepare that data set later. And in this case, oh, yes, I also told you that the intercept is the average, well, is the mean value for the zero group, right? In this case, for the white Americans that are here in this data set, right? I also explain you this plane, right? I told you that these are three variables from a regression line that you can see here. This is the regression model, right? Remember, depression is our dependent variable, and rumination and worry are our independent variable or predictors. So in this case, what I wanted to see is to evaluate if rumination and worry were related to depression, right? And what is the magnitude of the relationship? And what I did was a plot, a 3D plot where you can see, right, how it is a little bit tilted. The inclination is towards this area right here, because most of the people are healthy. These are C-scores, and remember that if you see -1, -2 in a C-score scale, that means that these people are located -1 or -2 standard deviations below the mean. So that means that they are below the mean on everything in this case, right? These people are very healthy. They are below the mean on rumination, below the mean on depression, and below the mean on worry. So they don't worry, they don't ruminate, and they don't really actually have a big concern on depression symptoms, right? So they are fine. While these ones are the people who you can see they are the worst, because even this guy right here, he's giving a nightmare. Well, he or she is living a nightmare. He or she worries a lot, right? He or she has a big level of depression, and he or she also ruminates a lot. So this person right here is somebody that we should pay attention, especially because he or she was a teenager. But I didn't collect data on names. This data set doesn't have names. Of course, that was not ethical. That was not part of the process. So I don't know who was this person, right? But that person probably is a red flag in this data set. Now that I see it better, I should have said something back then. Well, it's fine. That's how it happens. Hopefully, she or he's fine. Part of the mistakes that I made when I was starting as a researcher. I told you as well that you could standardize your estimated coefficient, your estimated slope, right? By following this formula right here. And you could do it by hand, like I did here, or you can trust any other package in R to do that. And I will show you other packages later in some of the assignments and practices. You don't have to do that by hand. I mean, this is 21st century. We don't have to do many things by hand. We can actually use software to do that, right? And we will do that. I just want you to know that that models are not will not show you the standardized solution by default many times. Sometimes you have to specify that, right? And it's very important to know that, because otherwise you might make the wrong interpretation of the output. And that's very bad, right? If you don't know what is the scale of your interpretation, if you don't know what is the metric of your slope and your intercept, you might arrive to the wrong conclusions. So that's something that you have to also always keep in mind. Now, this is something new. I told you that this is something that we call the classical regression model, and some people also call it the linear regression model. Why they use linear? Well, because it was thought to be a linear model, right? So, and for many years, we estimated only linear models. But given that we have computers now that are very powerful, we don't have to stick only with linear models. We can also estimate, for example, quadratic models. So I don't know if you remember this from algebra. I don't know if you remember polynomials in algebra. Um, and probably when you were studying that, you were thinking, oh, this is useless. I will never use this in my life. Well, you're wrong. That's everywhere. Algebra is everywhere. And everywhere that you are doing is actually based on algebra or calculus. So in one of the things that we use a lot in statistics is, is algebra in statistics, right? So this is a polynomial. This is part of the function. But this creates something that we call a quadratic function, right? And how it looks like? It looks like this. So when you square your term, and that's what I did here. Look at that. Let me show you this formula right here. So in here, I'm predicting wage, like I did before, right? And I'm using h as my predictor. So wage is my dependent variable, and h is my independent variable or predictor. But look at that. I added another term to my model. I'm saying that I'm squaring h, right? So now I'm estimating the square effect of h. That will create a quadratic function, right? And now it's not going to be linear anymore. And you can see it in this plot right here, right? Now the line, remember that the line used to be straight? It's not straight anymore. And actually, that's a better model, to be honest. Because look at this data. It doesn't look like a straight line. I mean, just by plotting, just by creating a scatter plot, you can see that now a linear model is not the best for this data, and actually it is not, right? What we see in reality is that people are getting more money over time, right? But there is a point in life when they are getting less money, right? Probably they didn't have a good pension, right? A very good retirement fund, or something happens in life, and actually the tendency is to get less money over time. If you keep it linear, you will assume that, oh yeah, look at that. If it is linear, you will be saying, actually, when I try to draw a straight line here, you will be saying that if you get older, you get more money, which is not kind of true, right? I wish it was like that, but many times it's not like that. So your income might change, right? Your wage will change. And also, people change jobs. Sometimes they change a job for a better life, and so they get a better job. Or sometimes they have to make decisions where they have to get a, a job where they get less money. So life is complicated. So of course, we cannot assume that people get more money um, over time, right? Over age. And look at this. Now we have a new term right here that says minus 0.5, minus 0.05. So, oh, am I being frozen right now? Um, can you see me fine? Mm, well, hopefully you can. Okay, for some reason I see something weird, but that's okay. Um, I'm assuming you can hear me, right? Yes, right. It's a little bit blurry. Well, okay, that's okay. It doesn't matter. It's just I don't want to I don't want to be dropped from the meeting. Okay, now you can also add more terms to the equation. Look at that. Now it's a cubic term. Thank you, Camilo. Thank you so much. Um, so look at that. We now have a quadratic term and a cubic term at the same time. And that will create this beautiful plot right here. But look at the line. The line is way more flexible now, right? But still, it looks like a trend where people are getting more money over time, and then it kind of slows down, right? They don't get more money, kind of get establishes there. And at the end, we don't have a lot of people, right? So that's why the line looks a little bit weird here. And actually, this is not the best model for this data, even though we try to fit this into this data. I would say that the quadratic model is the best model for this data, because it kind of adjusts better, right, the line of perfect fit to the data, right? So it's way smoother compared to this one. And of course, you can add more terms, right? For instance, you can add a fifth level polynomial, but by doing that, there is not a lot of difference, to be honest, from a quadratic term, right? It kind of flattens a little bit that trend towards the middle of the distribution, and then it slows down, but that's not the best model. Actually, this is something that we call saturated model. What I'm doing is estimating all the polynomials that I can, right? But that is not always good. There is a point where you have to stop adding polynomials because you can overfit a model. Once we have more time, well, probably in the last two lectures in this course, we're going to talk about overfitting a little bit. Because it's true that you can add as many terms and as many polynomials as you can, of course. But that also means that you are saturating the model. And when the model is saturated, it's actually meaningless. So, like everything in life, right? Things have to be just the right amount of the right amount of explanations in order to work. If you add a lot of possible explanations, it's hard to understand your model, right? And that's why in science we prefer something that is more parsimonious, something that um, is easy to understand and it doesn't overcomplicate things, right? It doesn't mean that we cannot estimate complicated models. We can, but our capacity to understand what is happening is reduced. But we will talk more about it probably if we have time. And there are some statistical implications of overfitting a model. Cool. So let me jump into Jamovi. I want to show you how you can do a regression model in Jamovi. I know that some of you don't have uh, Jamovi in your computer, especially the people who are using Chromebooks, but I will help you, of course, to install Jamovi in your computers. Oh, let me just delete this. Right. And then just this. Okay. In Jamovi, you can actually open any oh, what happened here? No, sorry about that. Zoom just dropped the sharing screen, but now it's working fine. So here in Jamovi, you can go to open and go to browse, And let me check where is the data. I believe it should be on lecture 9. Yes, right here. So if I open the wage data, oh, if you want to follow this as well, I believe I added, let me just go here. If you go page m-squared.net, right, or m-squared.net, to download the data from here, wage data right here. I was afraid of this. Can you hear me now? Yeah. Okay. I'm gonna assume you can. So I'm gonna just you can download the data from the link, and you can just click on download right here, right? So let's come back to Jamovi, right? So in here, we have all these variables, the same variables that we open in R. It's exactly the same. Actually, Jamovi is running R behind the scenes. It's doing everything in R, but you don't see it because it has a beauty. R is really working behind the scenes. So in here, in this tab, you will see the variable names, right? You can actually add labels to here. I can say is when participants answer the survey, right? You can add descriptions to your variables, which is very useful, right? You can add any description so you know what you are measuring in each of these variables. And also there's a tab for data, right? So in here you can see the data set as a data frame, like we always do in R, right? And now let me show you how you can fit a regression model like the one that we did before, or the several ones that we did before. So, for example, here, you can go to analysis, and then you go to regression, and you go to the section where it says linear regression. And this will open this menu right here. So there is a box for dependent variable. So for the dependent variable, we are going to use a wage, right, like we did before. And under covariates, you can list all the variables that are continuous. In this case, we don't have continuous variables. What we have is nominal predictors. So we are going to add race, for example, under factors. And look at that. It automatically estimated the regression just by adding the variables right here. And you can see they're the same numbers that I got from R. Of course, they should be exactly the same, right? And also, if you go to, for instance, model coefficients, you can ask for the standardized solution, right? And this is the standardized estimate. In this case, it doesn't make sense too much to do standardization for a nominal variable, but when you have continuous predictors, of course, it makes more sense to standardize the estimate. So it will create a new column here that says stand.estimate. So this new column will give you numbers that will range from -1 to 1, like a correlation, right? The closer this number gets to -1, for example, stronger is going to be the relationship between, for example, well, in this case, between our dummy variable, in this case, and our dependent variable. But remember, this represents the mean difference. So that's why it's weird, because this is the standardization of the score. So this is talking about standard deviations below or above the mean, right? So that's why in this case, it is not the best choice to standardize everything. It's better to keep it raw. But still, you could do it. And there's nothing wrong about it. And look at the table. The table in Jamovi, I don't know if you can see it. Hopefully you can. It's just I cannot zoom in Jamovi. It doesn't have any option. But look at that. It has a note right here, a footnote that says intercept represents reference level, which is awesome, right? So now you know that the intercept represents the reference level because you're working with nominal data. Also, you could go to Model Builder. No, actually, it's here, reference levels. And you can change the reference group. I remember that in the last class, Jennifer asked, well, should we use white as our reference group all the time? And the answer is no. You could change the reference group. In Jamovi, it's just a click. For example, I change it to black. So now I have the mean difference, right, versus black people. So for instance, white versus the people who are white versus black are getting $11 more, right, compared to black people. Asians are getting $18.7 more compared to black people. And other people or other races are getting minus $11.6 compared to black people, right? So if you change the reference group, of course, the numbers will be different because you are using a reference group that is different, right? Of course, the p-value is going to be the same in the sense that it's the same, it's going to be the same statistical inference. The only thing that changes is how you interpret the mean difference and the intercept, of course, right? Also, in here, you have a tab for assumptions in the regression model. I haven't talked with you yet about how to check that, but we will, I believe, today if we have time. So, for example, it will create a normality test for the residuals, right? And of course, it's telling me that the residuals don't come from a normal distribution, which is totally fine because I'm using nominal data. Of course, it shouldn't be normally distributed. So, of course, it's telling me, hey, now your residuals are not coming from a normal distribution, and that's totally fine and expected. Once we add more predictors, things will change. We can also do the regression model that we did before, right? Instead of using race, we can use H, right? So this is exactly the same regression that we did before. And let me see if I can do plots right here. Look at that. This is one of the things that I don't like from the software, and is that it's not easy to create plots for regression models. Let me check. Marginal means. No, the only way to do that is by going here under exploration descriptives. No, actually, Jesus Christ. Sorry about that. Exploration scatter plot. That's what I need. This is the only way. And wage. And this is how you create your scatter plot with a line of perfect fit. And it is hard to see it. Yeah, well, you can kind of see it there. The linear function, right? So yeah, Jamovi is not the best. That's why I like R. But that's how it is. Those are the things that Jamovi can do. Right. Well, as you saw, well, there are big differences between Jamovi and R. And the big difference is that in Jamovi, you can just click and click and click, and you get to the solution. However, if you want to come back and do the same, you might forget, right? Because there is not a script. There is no something where you can come back and see, oh, I did this no time ago, because you have a script. You have something where you can check, which is the case of R. But in Jamovi, there is no script. So that's the downside of using this type of software, right? It's easy, yes, it is. But it is hard to modify the defaults, right? It has some defaults, and you cannot modify those defaults. In R, you can modify anything you want, which makes everything easier. All right, let me just come back to right here. All right, well, let's have a break. Let's have a little break. Let's come back at 11. If you're fine with that. I need to take some medicines for my coughing. So let me just get 10 minutes and I'll be right back with you. Otherwise, I will be coughing a lot right now. Thank you. Right here. So the idea was to do a three-part regression lecture. However, I believe I'm going to be adding more. Let me just do the chat here. Oh, Jennifer's asking, how can I know my laptop has Jamovi? Well, if you don't know, probably you haven't installed Jamovi, or I don't know if we did it, Jennifer, together. But if you have it, you can go to the little magnifier or the search bar on Windows and just type Jamovi, right? Like this. I'm just typing the name on the chat, right? And if you don't have it, if it doesn't appear there, you don't have it. So you would have to install it. You can just, if you need to install Jamovi, remember, you can just go to Google and just type, for example, Jamovi download, and then go to Jamovi desktop, and then click here, right? If you have Windows, it will say another thing, right? It would say that there are two different versions for Windows. You can use either version, it's fine, it doesn't matter. In my case, it doesn't say that because I'm using Linux in this computer. So of course, it's saying that I need to install other things. But in your case, it would say here that you have Windows, and then you click, and that's it. And remember, you have to download Jamovi desktop. They also have something called Jamovi on the cloud or something like that. Don't install that one, or don't follow the instructions for that one. That means that you will be using Jamovi on the cloud, and that version is totally limited by the amount of variables. So of course, that's not the one that you need. You need to download the one that says Jamovi desktop, right? Oh, I was gonna say our next lecture is this one right here. That one that says Correlation and Regression Models Part 3. You can go to the web page or just go to Canvas, and it's gonna be there too, right? So in this part, I'm going to talk more a little bit ANOVA. Are you familiar with ANOVA, or analysis of variance? Have you heard about it in previous stats classes? No? No, right? No, probably, yes, probably you haven't heard about it. Oh, and I have more questions here. Is it Jamovi solid or current? It doesn't matter, Camilo. You can use solid or current. It doesn't matter for this class. Either way should work fine. So pick whatever you want, to be honest. It doesn't matter. The difference is that the solid version is the one that was updated long time ago, and current is a version that is updated every 2 months. But we don't need something that is current. Not necessary. You can install just the solid version. I have another question here. It says, will there be an exam the next week? No, that's a good question, Rosanna. No, not yet. I still need you to do other exercises with regression models. So no, the answer is no. Actually, I don't know what to do with that exam. Probably we're gonna do one single exam at the end of the semester, but no worries. As I said at the beginning of the semester, um, exams are not really exams in the sense that you have a time constraint and do the exam and it's timed, right? I don't do that. The exams are a little bit longer, but they are more like an assignment. I will give you instructions and you have to do things in Jamovi or R and answer some questions. Similar to the assignment number one. It's going to be very similar. So no, the answer is no. There's no exam the next week. Denise is asking, will there be a step-by-step video for Jamovi? And the answer is yes. Yes, there will be a video that is step-by-step for Jamovi as well. Yeah. Yes, there's always videos. There's always videos for everything in this class. So no worries about it. I won't leave you alone. Kind of. Laila said that she have heard about ANOVA, but she needs a refresher. So yeah, we're gonna do that. We're gonna talk about ANOVA. However, I'm not very big on ANOVAs. I'm very big on regression. So that's why I don't spend a lot of time explaining ANOVA. I really like regression models. And actually, those are the ones that have given me a lot of job opportunities just by knowing regression. I've been able to work in different fields, 4 different fields, and in different topics. So I would say that regression is way more flexible compared to ANOVA. However, ANOVA and regression, again, are exactly the same. Everything is about regression in statistics. Many of the topics that we study, at least in this class, are related to regression. Because ANOVA, it's another restricted version of regression. And we will see it. So regression, and let me just, yeah, I can use that one. Let me just move this. I hate this box. Wait a second. I'm trying to use the tools for drawing. Yeah, now it's working. So, as I'm saying here, regression is only one member of a big family that we called the general linear model. That's why the test and linear regressions are siblings, because they belong to this big theory that we call general linear models, right? And everything is part of the theory of regression. That's how it started. It started with theorems related to regression. And then little by little, ANOVA was born later on, and also MANOVA. ANOVA stands for Analysis of Variance. You can see here the name. And MANOVA stands for Multivariate Analysis of Variance. However, in this class, at least in my approach, I don't explain MANOVA. Why I don't explain MANOVA? Because it's useless. We have better tools now for understanding more complicated models. And MANOVA is not anymore a good model for that. It was useful a long time ago when we didn't have very fancy computers. Right now that we have very powerful computers, MANOVA is actually useless, to be honest. And we can do better models like structural equation models, random forest, and other things that we can do instead of focusing only on MANOVA. So I don't teach MANOVA. But if you want to know about MANOVA, of course, I can give you plenty of book chapters and articles about analysis of variance, but multivariate analysis of variance. But to be honest, it doesn't matter. Regression can handle everything. Analysis of variance, well, that one is a little bit more useful, especially if you are conducting experiments. and especially if you are from psychology. As a tradition, psychologists were very good at using analysis of variance models, or ANOVA for short, right? In psychology, actually, we use them a lot. While regression is very famous in economy, or for example, in health-related fields, right? Or at least that was kind of the tendency a time ago. Right now, well, we use whatever we can. So, of course, you will find, for example, some faculties here who really like ANOVA, and they will ask you to do ANOVA models. If they ask you to do that, just do it. It's fine. It's just regression. In other people will give you more freedom, especially when you're taking the seminars, right? So you will have more freedom to pick different models. And now you might be thinking, how do I select the model? What is the best model? Well, the answer is it depends on your design. It depends on the research project that you have in mind. And also it depends on how you want to communicate the information. So we will do a little bit of ANOVA, and I will explain you more about it. Oh, I should erase this. In ANOVA, we will have a null hypothesis, very similar to t-test, right? Remember that in t-test, we were evaluating the hypothesis that says that group one, the mean of group one is equal to the mean of group two, right? But now in ANOVA, we can have a third group, right? Now we can test the null hypothesis that says that the mean of group one is exactly the same as the mean of group two, and the mean of group two is exactly the same as the mean of group three. So as you can see, now we have multiple groups in our equation. In t-test, remember, we can have only two. But in ANOVA and regression, you can have more. Actually, it doesn't have to be only three. You can have 4, 5, 6, as many groups as you need. Of course, with limitations. You cannot add 20 groups if you have only 10 people, right? That doesn't make sense, right? Or you cannot have 30 groups and have 30 people, right? That means that one individual per group. That doesn't make sense at all, right? So there are limitations. It depends on the sample size that you have. But yeah, in theory, I mean, mathematically speaking, you can add as many groups as you need. Let's take an example, or let's see an example. Let's imagine that that you want to evaluate, or you want to see, or to test, that would be a better say. You want to test if there is a mean difference on wage when people are married. Well, when people were never married, when they were married, widowed, divorced, or separated, right? Because all these groups actually have a different wage, average wage, right? Look at the wage of never married people, right? It's 92.73, right? While look at the people who are married, they're getting more money, $118.86. That's a lot of money compared to the others, right? And you might be thinking, well, that means that they should get married. Well, I don't know. In this data, it says that. But probably it's because, I don't know, probably people who are married are working more, right? Probably they have two jobs or three. So the average wage is probably higher, right? It's not necessarily that because you are married, you're getting more money. It's not because of that. It's probably because you're working more, right? So, and you're getting a higher wage, but of course, you are spending more money. Yeah, perhaps. I don't know how. Yeah, Jennifer, you're right. Probably in this research, the way they ask about the wage was more like a household income question. I don't know, to be honest, but that could be possible too, Jennifer. Yeah. I don't know. I was no part of the design of this data, so I don't know. But yeah, that's also possible, Jennifer. Yes. So yeah, it doesn't mean that you have to get married in order to get more money. Well, that would mean that many people will get married very faster, way faster if they knew that they would get more money. So you can see that there are mean differences among these groups. Now we have to ask ourselves, is this difference explained by chance, right? We don't know, right? We see a difference. There is a nominal difference on this, but we don't know if this difference is explained by chance or not. That's why we need statistical models like ANOVA or regression in order to find out if that's true or not. So for this model, for the ANOVA model, we can ask the question, are the mean differences in wage by marital status explainable by chance alone, right? So we need to find out where is the difference. Now, ANOVA will tell us that, yes, there is a difference at the mean level. But after conducting ANOVA, we will need to do a pairwise comparison. You will see what I mean by that. But first, let's focus more on the nature of the ANOVA model. ANOVA is actually a linear model, like any other linear model that we study here. T-test is a linear model. Regression is actually well, it was thought to be a linear model. Of course, it can be non-linear, but in essence, it was thought to be a linear model. And also ANOVA could be a linear model, right? And what we have in ANOVA is an outcome, right? And we have the variance explained by the model and variance that is associated to error, right? There is error in our model. And if you see this, it's actually the same formulation of regression. It's exactly the same. We have a model. Remember that in regression, let me show you here. Oh, let me delete this. In regression, remember that we have y beta sub 0 plus beta sub 1 x1. Let's imagine only one predictor. And we have error. The same thing happens in ANOVA, right? In ANOVA, we have this part right here, right? And I call that model. This is what the model can explain, actually. Wait. This is what the model can explain. This is the portion that is accounted by the model. And the other portion that is error, which is something that we cannot explain, right? So both regression and ANOVA, they are the same. They are linear models. The difference is how the line of best fit is estimated, right? It's a little bit different. But at the end, both models are estimating the difference from the line of best fit, right? How good the line of best fit explains the data. Ah, yes, I always forget to. Let me just delete this. All right. So in ANOVA, and it's the same for regression, to be honest, accounts for the variances within your groups. So in ANOVA, we are going to care a lot about the variance within groups. And also calculates the variance that is explained by your model. So we have variance explained by my model and variability that is not explained by the model, right? There's something that we cannot explain. In ANOVA, we are going to estimate something that we call the total sum of squares. And in this estimation, what we do is to take each individual, well, each observation, right? And we subtract that from the grand mean, right? That's the total sum of squares, right? And, well, actually, I'm missing something here. Sum of squares. Yes, this should be. I'm missing a square root. Sorry, the square here. I'm missing the number 2 here. Yeah, I don't know why it's not there. Let me check. Oh, yeah, here it's right. Model sum of squares. Yeah, this is the model sum of squares. Yeah, but this one, yeah. Just pay attention that I missed the number 2 here. It should be here. I don't know why I didn't write that. Because it has to be the sum of squares. So I have to add them together. So yeah, I was missing the number 2 here. Sorry about that. Just bear that in mind. So in here, what we do is to take each individual and then subtract that from the grand mean. The grand mean is just the overall mean of your outcome. So let's put names to this. Let's imagine that I'm doing an estimation with wage, right? My outcome is wage. So I have a mean for wage. Let's imagine that the mean, I think it was around 112 point something, right? And I have, I don't know, I have Jennifer here in my data set, right? And Jennifer, I don't know, has a wage, I don't know, of $100, right? So what I do is to subtract 100 minus 112, right? The result, the product of this is going to be a square, right? And then that's 144. And then I'm going to add all these differences for each participant, and I'm going to get the total sum of squares. Why do we do this? Well, this is one way to do the same thing that regression is doing. So we are going to use this estimation, this estimated sum of squares grand mean, in order to have a proxy to the total variance explained by the model. So what we are doing is, through the sum of squares, get an indicator of the total variance explained. We're gonna change this into something else later, but this is kind of the first step, because we need to account for the total variance of the model. In regression, it does exactly the same. In here, well, I did it by hand, right? This is the estimation of the total sum of squares right here. In this case, I'm using the wage data. Yeah, right. This is the total sum. It looks like a huge number, but this number is going to be used later in a transform way. Now we can also, well, we need to estimate the model sum of squares. So notice what I'm doing. What I'm doing is, or what we do in ANOVA, is to get the total of the total variance explained, or the total sum of squares, right? And now I'm getting the total of my model, right? So this is like all the possible information that you can explain. And now I need an estimation of what I really explain, right? So that's why I need this little guy here. And we are gonna do a division later. That's gonna be a ratio between these two, right? Because it's just that. It's just trying to quantify how much can I explain and how much I really explain by my model. And how do we do that? Well, the model sum of squares, what it's doing is taking the mean of each group am subtracting the mean of each group minus the grand mean. So, for example, let's imagine that I don't know, the divorced people, I don't remember what was the income. It was like $90, right? So divorce minus 112, right? And the result is gonna be squared, right? And I'm gonna do the same for all the groups, right? What I do is take the mean of each group minus the grand mean. Then I square the term. I multiply that by the number of individuals in each group, right? And then I add all these together. And that will give me actually a big number. And K in these mathematical formulations represent each group, right? So K in this case is, for example, you have to do this for the divorced people and then get another number for people who are married, people who are widowed, people who are separated, and so on, right? Because they are different groups. So you will do the same for each group. And at the end, you add them all together. So what we are doing here is trying to explain the variability inside the group, right? Or isolate that, at least, to have an indicator of variability inside the group. Well, actually, outside the group, to be honest. It's more the variability between groups instead of within groups. Now we need to estimate the sum of squares of the residuals. So what we do, did it, oh, what happened here? It drops my sharing screen. Okay. Okay, now you can see it probably. So as I said, this is the formula for estimating the sum of squares of the residuals. And what we have is each individual in each group, right? And we subtract the score of this individual in this group minus the mean of the group where the individual belongs. So let's come back to an example. So let's imagine, I don't know, let's imagine, I don't know, Denise belongs to the married group, right? So Denise has an income of, I don't know, $115 per, I don't know, yeah, probably $115 per hour, right? And then we subtract that from the mean of divorced people, which in this case, I don't know, it was like 95, right? And of course, this would give us a negative number that is going to be squared, and now it's going to be positive. And then we do the same for each individual in the group of married people, right? And then we do the same for each individual in the group of divorced people and widow people and other marital status, right? So why do we do this? Well, what we are doing here is quantifying the portion of the model that, well, the portion of the variance that is not explained by your model. Because in here, what we are saying is that I cannot explain the variation inside the groups. I'm explaining the variation between the groups. So how different is group, married group versus non-married group, or divorced people versus married people, right? But I cannot explain the variance inside each group. Whatever is inside each group, I cannot do anything. And that's one of the limitations of ANOVA, right? But there are other models that will actually account for the variance inside the group and outside the group. But this model is not a model for that. This only will tell you differences between groups. That's the only thing it does. And that's okay. Many times that's the answer that we need. But other times we need to go further and also get the information about what is happening inside each group. But that's a story for another day. And for another class. That's something that we call multi-level models or random effects models. But that's a story, as I said, for another type of class, a way more advanced class. Let me just delete this. Okay, I already said this. Nice. Now, time for an example. This is how you would run a ANOVA model in R. Now we are not using the function lm anymore. We are using the function AOV, that stands for ANOVA, right? But the formula is the same, right? Look at that. I'm just doing wage, and my predictor is marital status, and it's a grouping variable. And notice something that is interesting here. I don't have to do dummy coding variables, because ANOVA understands that whatever you put here is normally a factor or nominal variable. So when you're doing ANOVA, you don't have to do dummy coded variables like we do in regression. That's one of the big differences. And that's why many people prefer ANOVA. They don't have to do dummy coded variables, right? But to be honest, the answer is going to be the same. Let me check if I have questions in the chat. No, it's fine. Right, so let's see what happens here. So in this table, we have two lines or two rows here. We have a row for our independent variable, marital status, and another row for residuals. That's it, right? It doesn't look very sophisticated. Why? Because what we are doing is estimating the information because of the model and the leftover out of the model. This is the variance. This is the equivalent to variance, and it's something that we cannot explain, right? But let me explain you more about this table later. Let me explain you something here. Right now, we know because of something that we call the F test, that I will explain little by little. But because of this test, I have a p-value, and this p-value is very small. That means that at least one mean is different from the other. Remember that we have here, how many groups? We have 5 groups. And it's telling me that at least one difference, one mean is different from the other, and that difference is not explained by chance. That's what it's telling me. But I don't know which is the mean that is different, or what combination of means are different from the others, right? So I don't know. This is something that we call a omnibus test. A omnibus test will tell you if overall there is a difference between means, right? And the answer is yes, there is a difference, and the difference is not explained by chance. But at this point, I don't know where is the difference. So let's take a look at these box plots right here. Remember, box plots are very useful when you want to see patterns between groups, right? So for example, in this plot, I added this red dot. The red dot is the mean of each group, and this bold line is the median of each group. So as you can see, this group is the one that is getting a lot of money compared to the others. And this group is the married people. While never married, well, it's a little bit different from the others too. But look at these groups right here, these 3 groups. They are practically the same, visually speaking, right? Look at that. The median is very close to this median, and this median is very close to this one, and the mean is actually very close to the others. So we could think, hey, probably the mean difference that the omnibus test is detecting is located here, right? Probably is detecting, you know what? Married people are getting way more money, and that is not explained by chance. Probably. I don't know. That's why we always need to display our data in a plot, right? In order to find out. So we can visually evaluate that, and also we can do something called pairwise pairwise evaluation or pairwise test. Why is pairwise? Because I take a pair of means and I test if the difference is explained by chance or not. So for example, in this table, I have the mean difference between married and never married people, right? The mean difference is 26.13. It's just a subtraction, right? I'm just subtracting the mean of married people minus the mean of never married people. And then I can get a p-value with a mathematical formula that I didn't add here because I thought it was not necessary for a psychology class, right? But there is a mathematical formulation for this and how you do it, but the software will do it for you. So I don't need you to know the mathematical formulation, but there is something behind. This pairwise contrast or pairwise comparison will give you this p-value right here. So look at this. In this case, it's telling me that the mean difference between married people and never married people is not explained by chance, right? And actually, let's take a look. The difference is kind of big, so probably that's why it's not explained by chance, right? Let's see the other line. The other line is comparing the mean of widowed people versus males who were never married. However, this difference is explained by chance because the p-value is way larger than 0.05, right? It's almost 1. So of course, this difference is explained by chance. But let's take a look at another one. Divorced versus never married is actually not explained by chance. But if we continue going, for example, divorced versus widowed, separated versus widowed, and separated versus divorced, they are all explained by chance. Sorry. They are all explained by chance. And actually, that's what corresponds to the comparison of this box versus this box, and this box versus this box, right? And this box versus this box right here. So all these guys, well, they're very similar, right? And it makes sense, right? So that's why the test is telling us, you know what? There is a mean difference, but it's so tiny that it's actually explained by chance, right? And we can see it in this plot right here. Now, you could be thinking right now, can I do a pairwise comparison in regression? And the answer is yes. You could do exactly the same in regression. But many softwares will add some features that make the ANOVA estimation easier compared to regression. In regression, you would have to do some other operations in your data set, while in ANOVA, you can just use the variable that you have in your data set, put it into the software, and the software will do everything for you. So that's why many psychologists love ANOVA, because they don't want to deal with a lot of transformations in their data. So, and a lot of things that they have to do later in regression. So that's probably why they don't like. It's like driving a automatic car, right? You want just to drive, sit and drive, right? You don't want to shift gears or know how to shift gears. Well, ANOVA works like that sometimes. Like you just sit there in front of the computer, you add the independent variable, the dependent variable, and voila, you have a result, right? And it's fine if that's what you prefer, because I imagine that you will not be data analysis. At least most of you will do different things in your life, and that's okay. Questions so far? It will make sense later, once you analyze more data, once you have the chance to sit with the data that I will provide for you, and you will have to analyze the information. Now, what time is it? Okay, I have 10 minutes. That's nice. Let me just delete this. remember that in t-test, we were using the t-distribution, right? I told you that the t-distribution is a better distribution for in order to account for differences between groups, right? And that's why we use it. We use the t-distribution, and that's why the name of the t-test is t-test, right? In ANOVA and also in regression, we are going to use the F ratio, which translates into a F distribution, right? We love letters. I told you, R, T, F, letters is better, it's easier. F stands for Fisher. Sir Fisher was the guy who kind of coined or found the density for the F distribution, right? So that's why it's called F for Fisher. So the F distribution is a distribution that looks very similar to the normal distribution, to be honest, and very similar to the T distribution. You will have values, negative values and positive values. It doesn't have zero all the time. In this case, the simulated values that I created, of course, they are more towards zero, but the mean could be located at different places, right? The mean could be more skewed, so it could be around 5. It depends on how you simulate, of course, this plot. This is the distribution that will help us to find the p-value. So this is the distribution for our null model. I will use this function, well, this probability function, which is, in other words, the distribution, right? Oh, actually, this is the t-test. Sorry, this is the t-distribution. The F is right here. I was like, well, that's weird. F should be skewed. This is the F distribution. Sorry about that. I wasn't. Something is weird here. Yeah, this is the F distribution, right? So F tends to be actually, yeah, this makes more sense. I was like, wait a minute. Doesn't make sense. Here, in here, in this simulated data, I have positive values, right? And actually, the F value only has positive values. It cannot be negative. So it's only positive values, while the t-test could have negative values. That's correct. Yeah. And the mean could be, as I said, yeah, located at different places. In this case, is located at around 0 point something. I don't know where is. Oh, yes. It's around, well, 5, like 4 point something right here. Yeah, like around 4 is the mean. It's kind of a weird distribution. So in this distribution, we will find the area under the curve. And the area under the curve will tell us the value for our p-value. The F distribution will have 2 parameters. We'll have something that we call degrees of freedom, and the degrees of freedom will have numerator and denominator. It's more like a fraction, right? So if you see my code here, I have 2 values right here. So this is the numerator and denominator right here. So these are degrees of freedom. The degrees of freedom are more like shape parameters, are telling to the distribution how the shape is gonna be. So for example, and actually, let me just copy this part. Let me go to R. Actually, all this part. Jesus Christ, don't do that. Let me just go here. Let me just go to R very quickly. If I run this with different values, right? Let's imagine, I don't know, 8 and 20, and I run this, the shape is going to be a little bit different, right? And let's imagine that I do 2020. Look at that. It is moving a little bit, right? It kind of changes the shape of this distribution. It doesn't have a mean, but of course you have an expected value, but it's not exactly like the mean of the normal distribution. It's a little bit different, right? And if you have larger values here, it starts behaving more, well, actually, right? Larger values on both degrees of freedom. Look at that. It starts behaving more like a normal distribution, right? It kind of becomes more like a normal distribution because they are related. The F distribution, the T distribution, and the Z distribution are kind of related to the normal distribution a little bit. And yeah, bigger values here in the numerator and denominator will give you a bell shape like style, right? So it kind of shifts a little bit. So these degrees of freedom are also another way to quantify pieces of information. Pieces of information are related to how many parameters you can estimate, right? Degrees of freedom will tell you if you have enough information in order to estimate the model that you want to estimate. That's why we also use the F distribution. And that's why we call this the F test sometimes, or the F ratio test. And I should stop here because it's almost 11:50. So let's stop here. And please stay here if you have questions. Let me stop sharing. And I'm gonna start.